Hello and welcome to my science tutorials. In today's video, we want to look at series resonance, where we'll be talking about resonant frequency. Before we begin, if you're new to my science tutorials, kindly consider subscribing and turning on the notification button so that you will stay updated of any of our latest tutorial that we'll upload in the future. So without further delay, let's begin. Now, in our previous tutorial, we did mention or we talked extensively about RLC series AC circuit, where we said this is just a circuit having a resistor, an inductor, and then a capacitor connected in series. Now, when we were looking at this resistor, inductor, capacitor circuit, we came to a point where we were talking about capacitive reactance and then inductive reactance. We said that there are three things that can happen. The first one is we can have our capacitive inductance to be greater than the inductive reactance. The second one is when we flip this guy, so we can have our inductive reactance being greater than the capacitive reactance. Now, the third phenomenon that can happen is when we have our inductive reactance to be equal to the capacitive reactance. And when we have this phenomenon occurring, we describe this phenomenon as resonant series resonance. So this is where series resonance occurs. So in the point where we have an RLC series circuit where the capacitive inductance is equal to the inductive reactance, we said at that point we have something we call series resonant, and the frequency at which these two guys are equal is what we are calling the resonant frequency. Now, at this series resonance, there are a couple of things that happen. At series resonance I, we realize that the inductive voltage will be equal to the capacitive voltage. That is one of the things that happens. Secondly, we realize that the impedance of the circuit is equal to the resistance in the circuit. And then from there, we realize that instead of using V is equal to IZ, which we normally use in an RLC series circuit, we can also use, or this is equal to V is equal to IR, just using the resistance of the resistor in that particular circuit. So it means that this guy and this guy are in phase, so they cancel each other out, and then just the resistance in that particular RLC series circuit becomes the only opposition to the flow of current. So your impedance will be equal to your resistance, as we stated over here. Now, because we are having our capacitive reactance to be equal to the inductive reactance, let's look at what happens. So when XL is equal to XC, we know that mathematically XL is given to us as 2 pi FL, and this is equal to our capacitive reactance is equal to 1 over 2 pi FC. Now, the frequency at which the inductive reactance is equal to the capacitive reactance is what we are calling the resonant frequency. So we are representing the frequency over here by FR. So let's try to make the frequency the subject. So if we cross multiply over here, we are going to get 4 pi squared resonant frequency squared LC, that is this multiplied by this, is equal to 1. Now, because we want to make resonant frequency the subject, we divide both sides by 4 pi squared LC over here to by 4 pi squared LC. So we have resonant frequency squared to be equal to 1 over 4 pi squared LC. Now, to get rid of the square sign which is attached to the resonance frequency, we bring a square root, then a square root over here. So this cancels this. So we have the resonant frequency to be equal to the square root of 1 is still 1. So we have 1 over the square root of 4 pi squared, okay, is equal to 2 pi, because 4 here is 2 squared, pi squared is also pi squared, so we apply the root sign, it will be 2 pi. Then the only thing that will be left is just the root sign being applied to the inductance and then the capacitor. So this is what we get as our resonant frequency. So our FR over here is what we are calling the resonant frequency. The resonant frequency. We know that our L is our inductance of the inductor. Our C is the capacitance of the capacitor. All right. Also, in this series resonance circuit, we often describe the circuit as an acceptor circuit, since it is at this point that the minimum impedance occurs and then the maximum current is also given out. So at resonant frequency, the resistance to the flow of current is at the minimum. Because it's at the minimum, the current experienced at this point is at the maximum. It's at the maximum over here. So the keynote over here is that when we have an RLC series circuit and then we have this third condition being met, where we have the inductive reactance being equal to the capacitive reactance, we say that that phenomenon is called series resonance, and then the frequency at which it happens is what we are calling the resonant frequency, and that is given mathematically as 1 over 2 pi the root of LC, as we can see over here. So let's go ahead and look at some questions to see how we apply or we use resonant frequency in calculation. Okay, so we have example number 1. A coil of resistance 10 ohms and an inductance of 125 millihenry is connected in series with a 60 microfarad capacitor across a 120 volt supply. At what frequency does the resonance occur? Find the current flowing at that resonant frequency. Very good. So this is very easy for us to do, straightforward and pretty easy. So let's write down our solution. Now, the first thing we need to note is to write down our parameters to see what we have, what we don't have, and then how we can proceed forward. So we have a coil having a resistance of 10 ohms. So we have our resistance is 10 ohms. And then we're told that the inductance L is 125 millihenry. And then it's connected in series with a capacitor of capacitance 60 microfarad across a voltage of 120 volt supply. We're asked that at what frequency, or the resonant frequency, does this occur, and we are also to find the current at which this occurs. All right, this is pretty easy, pretty straightforward. We stated the fact that at resonant frequency XL is equal to XC, where we went ahead and found out that the resonant frequency FR is equal to 1 over 2 pi the root of LC. So from here we can go ahead and find our resonant frequency to be equal to 1 over 2 pi root. The L, which is the inductance given to us over here, is 125 times 10 raised to the power negative 3 multiplied by, we have our capacitor having 60 times 10 raised to the power minus 6 over here as the capacitance over here. So our resonant frequency is equal to 1 over 2 pi the root of 125 times 10 raised to the power minus 3 multiplied by 60 times 10 raised to the power minus 6 will give us a frequency of 58.12 hertz. Okay, so the 58.12 hertz is now the frequency at which the resonance frequency at which the resonance is occurring. So this is our resonant frequency. Now we also to find the current at which the resonant frequency occur. Now ideally we are to use V is equal to IZ. That means we need to find the impedance of the entire circuit using the capacitor, the inductance, finding the inductive reactance and then the capacitive reactance, and then using the formula Z is equal to the root of R squared plus into bracket XL minus XC squared. But remember, I said that as at resonant frequency, I said that XL is equal to XC over here. And when that happens, we realize that our impedance is equal to the resistance in this entire circuit. So that means that we don't need to find the impedance, as the impedance is equal to the resistance. So it means we can use voltage is equal to IR, and we can use that to find our current. Now we're told that the resistance in this particular circuit is 10 ohms, and we're given the voltage to be 120 volts. So we have 120 is equal to our current is still here, I, multiplied by the resistance is over here is 10. So if we divide both sides by 10 and we cancel that out, we have our current to be equal to 120 on 10 will give us 12 amperes as our current over here. Alright, so let's have a look at the second example. We have the current at resonance in a series RC LCR circuit is 100 microamperes. If the applied voltage is 2 millivolts at frequency of 200,000 hertz and the circuit inductance is 50 microhenry, we have to find the circuit resistance and then the circuit capacitance. Alright, so let's go ahead and look at all the parameters that we have in this particular question. So we write down our solution. We're told that the current in this particular circuit is 100 microamperes. So 100 times 10 raised to the power minus 6 amperes. And then we're told that the voltage V is equal to 2 times 10 raised to the power minus 3 volts. The frequency, which is the resonant frequency, is 200,000 hertz. And then we're also told that the circuit inductance, which is L, is equal to 50 microhenry. We have to find the circuit resistance and the circuit capacitance. Alright, so let's go ahead and look at what we can do. Now, for us to find the circuit resistance, we know that voltage V is equal to IR when we have resonant frequency occurring. So we have the voltage, we have the current, we can easily find our circuit resistance. So our voltage here is 2 times 10 raised to the power minus 3 is equal to our current here is 100 times 10 raised to the power minus 6 multiplied by our resistance R. So if we divide both sides by 100 times 10 raised to the power minus 6, we can get our resistance R to be equal to 2 times 10 raised to the power minus 3 on 100 times 10 raised to the power negative 6 is going to give me 20 ohms as my resistance. So my resistance in this case is 20 ohms. Alright, so now let's go ahead and find the circuit capacitance. Now, for us to find the circuit capacitance, we know that resonant frequency FR is equal to 1 over 2 pi the root of LC. Okay, so we need to make C the subject over here. So we need to do a little bit of change of subject. So if we cross multiply here, we realize that we have resonant frequency multiplied by 2 pi the root of LC will give us 1. So we divide both sides by resonant frequency multiplied by 2 pi. Resonant frequency multiplied by 2 pi. We will be left with the root of LC is equal to 1 over resonant frequency 2 pi. So we square both sides to get rid of the root sign. So we have LC is equal to 1. Okay, so we squared both sides. So 1 squared is still 1 over resonant frequency squared 4 pi squared. That is if we square both sides. So that implies that our LC is equal to 1 over 4 pi squared resonant frequency squared. Okay, so we can divide both sides by L for us to get our C. So if we divide both sides by L, our C will now be equal to 1 over, if we do this computation very well, we are going to get 1 over 4 pi squared resonant frequency squared. This is divided by L, okay, so it will be multiplied by 1 over L. So we have the L will now come at the denominator over here. So we can go ahead and find our capacitance, and this will be equal to 1 over 4 pi squared. Our resonant frequency we were given is 200 times 10 raised to the power 3 squared. Don't forget that. And then our inductance is 50 times 10 raised to the power minus 6. Okay, so if we do that and we compute that, we realize that 1 over 4 pi squared multiplied by the resonant frequency squared multiplied by the inductance is going to give us a capacitance, or our C will be equal to 1.267 times 10 raised to the power minus 8, which we can rewrite as C to be equal to 12.67 nanofarad. So this is now our circuit capacitance. Right, so let's go ahead and have a look at one final example. So the last example in this tutorial, I want to find the resonance frequency of a series AC circuit consisting of a coil of resistance 10 ohms and inductance 50 microhenry and capacitance 0.05 microfarad. Find also the current flowing at resonance if the supply voltage is 100 volts. This is also very easy. So let's write down our solution. As usual, let's write down all the parameters that we have to see what we are lacking and where to go from there. So we're asked to find the resonance frequency FR, so we do not know that. And then we were told that the resistance, okay, a coil having a resistance of 10 ohms, and then an inductance L of 50 millihenry, and a capacitance C is equal to 0.05 microfarad. And we're also, the question is also asking for us to find the current. Okay, we don't know the current flowing at resonance if the voltage supply is 100 volt. All right, so this is very easy. So the first thing we have to do is to find the resonance frequency. We know that resonance frequency is equal to 1 over 2 pi the root of LC. We have L, we have C, we know 2 pi, so it's easy for us. So resonance frequency is equal to 1 over 2 pi the root of, our L over here is 50 times 10 raised to the power minus 3 multiplied by our capacitance C is 0.05 times 10 raised to the power minus 6. Okay, so if we compute everything we have over here into our calculator, we are going to get 3.183 kilohertz as our resonance frequency. All right, so the second part of the question is demanding we find the current if the supply voltage is 100 volts. So over here we were told that V is equal to IR, and then we already know our voltage, that V is equal to 100 volts. We know our resistance to be 10 ohms, and then we don't know what our current is. So if we make the current the subject from here, we are going to get current will be equal to the voltage on the resistance, and this will be equal to the voltage here is 100 volts divided by the resistance. The resistance over here is 10, and so if we do that calculation, this will cancel this, and then 10 divided by 1 is 10. So we are going to get 10 amperes as our current in this particular example. So thank you so much for watching. This is the end of series resonant and how to calculate the resonant frequency. Up next, we'll be looking at how to calculate something we call the Q factor and then we'll also be looking at a combination of Q factor and then resonance frequency as a question altogether, and see how we can solve them. So thank you once again for watching, and I will see you in the next video. Bye bye. Hello and welcome to my science tutorials. In today's video, we want to look at resonance frequency and Q factor or voltage magnification. Before we begin, if you're new to my science tutorials, kindly consider subscribing and turning on the notification button so that you do not miss any of our latest tutorials on biology, chemistry, mathematics, and physics. So without further ado, let's begin. Now, in our previous tutorial, we made mention of the fact that in an RLC series circuit where we have a resistor, inductor, and a capacitor, if we have our inductive reactance being equal to our capacitive reactance, we establish the fact that at this condition, we say that the circuit is at resonance. And the frequency at which this resonance occurs, is what we are calling the resonant frequency. Resonant frequency. And we establish the fact that the resonant frequency is given to us as 1 over 2 pi the root of LC. Now, if we have resonance in our RLC series circuit and the resistance, or the resistance is small, so the resistance of the resistor is smaller than the inductive reactance or the capacitive reactance. If this is smaller than both XL and XC, another special condition occurs. That special condition, it is possible for us to have our inductive voltage, our VL, which we are calling the inductive voltage, and then our capacitive voltage, Now, when we have the resonance and then our resistance is smaller than the inductive reactance and the capacitive reactance, we can observe that our inductive voltage and our capacitive voltage will be greater than the supply voltage. And when this occurs, we see that there is a voltage magnification, or there is something we call Q factor. This simply means that when we have an RLC series circuit, so we have a resistor, inductor, and a capacitor connected to an AC source, and then we have our inductive reactance to be equal to our capacitive reactance, and our resistance here is very small. We are expecting that the voltage over here, assuming this is 20 volts, if this is the voltage supply or the supply voltage, it is possible for the voltage across just the inductor to be greater than 20, so something like maybe 30, and this guy, the voltage across the capacitor can be something like 40. So if we see this, we can see that the voltage across the inductor VL is greater than the supply voltage, which is 20, and then the voltage across the capacitor is also greater than the supply voltage. Now, when this happens, we say that there is a voltage magnification or Q factor. So how do we calculate that voltage magnification or the Q factor? So the voltage magnification is given to us mathematically as the voltage across either the inductor or the capacitor on the voltage supplied or the supply voltage. So it is the voltage, that the ratio between the voltage across the inductor or the capacitor to the ratio of the voltage supply. Now, this ratio is a measure of the quality of the circuit, that is as a resonator or a turning device, and we call that the Q factor. Now let's look at some calculations on how we can derive an actual formula that we can use for our Q factor. Like I said, the Q factor is equal to our voltage magnification. So let's look at how to do or how to derive a formula for voltage magnification. Now we said that this occurs at resonance, and then at resonance we have a resonant frequency, and then we also established the fact that resonant frequency is equal to 1 over 2 pi the root of LC. So this is at resonant frequency. We also established the fact that Q factor or the voltage magnification is the ratio of inductive voltage on the supply voltage. Okay, so this is equal to our inductive voltage will be IXL over our voltage over here, supply voltage will be IR in this case. So since the current are the same, this is XL over R. We also said that Q factor can also be the voltage across the capacitor over the supply voltage. So this can also be IXC over IR, which is also equal to XC over R. Okay, so this is the formula for both, but if you like you can further break them down. So XL is 2 pi FL over R, and XC is, this guy is 1 over 2 pi FC over R, and this will give you 1 over 2 pi FCR. Now remember the frequency here is resonant frequency, so it's FR. Okay, now let's look at something that happens and how we can derive a simpler formula for resonant frequency, for Q factor. Okay, so from here over here, let's make this our equation 1, this our equation 2. So from here, let's try to do something. Let's cross multiply. So if we cross multiply, we're going to have resonant frequency multiplied by 2 pi to be equal to 1 over the root of LC. So this means that if we have 2 pi multiplied by frequency, it should be equal to the ratio 1 over the root of LC. So let's make this equation 3. Now let's take one of this formula. So let me take the first equation, which is equation 1. So taking equation 1, let's do some substitution. We say that Q factor is equal to 2 pi FRL over R. Okay, and we also established from equation 3, or using the resonant frequency, we realize that the 2 pi F here can be replaced by 1 over the root of LC. So let me rewrite that. This is 2 pi FR multiplied by L over R over here. And so in place of 2 pi FR over here, we can substitute this. So Q factor is equal to 1 over the root of LC multiplied by L on R. So this will be equal to L over the root of LC multiplied by resistance. Okay, so now let's break this guy down and see what we can have. So this is equal to, let me do it at the bottom here. So our Q factor will be equal to, let me factor out 1 over R. So I'm going to have 1 over R outside. Okay, then into bracket I will have L over the root of LC. Okay, this is still the same as what we have over here. So this is equal to 1 over R multiplied by L over the root of LC can be written as C raised to the power half L raised to the power half. Okay, because the root sign is power half. Okay, so if we do that, it means this is equal to 1 over R, then into bracket we have L at the top with the power 1, So we can bring this guy to the top. Okay, indices. So if you send this guy up, it will become negative. So minus half on C raised to the power half at the bottom over here. So this is equal to 1 over R into bracket. And we have L1 minus L raised to the power 1 minus half will give us L half on C also raised to the power half. And we know half is the root. So this finally is equal to 1 over R into brackets the root of L on C. The root is covering both because this is also raised to the power half, this is also raised to the power half. So at the end, we are saying that our Q factor can be given to us mathematically as 1 over R multiplied by the root of L and C. So this is the formula for our Q factor. Okay, so you can either use this formula for the Q factor, or you use the formula over here, equation 1, or you use the formula here for equation 2 if you have the resonant frequency and the other parameters. But this is a much simpler formula. So you can either use this formula over here, this formula over here to find your resonant frequency and the Q factor. So let's go ahead and look at some examples to actually appreciate what we are doing. So example number 1, a coil of inductance 80 millihenry and negligible resistance is connected in series with a capacitance of 0.25 microfarad and a resistor of resistance 12.5 ohms across a 100 volt variable frequency supply. We are to determine I, the resonant frequency, II, the current at resonance, III, how many times greater than the supply voltage is the voltage across the reactance at resonance, or simply put, the Q factor. So this is very easy. Let's write down our solution. Alright, so let me use another color for the calculation. Right, so we're told that a coil of inductance, so we have our inductance L to be equal to 80 millihenry, and we also have our capacitance C is equal to 0.25 microfarad, and then the resistor of resistance 12.5 ohms, and then a voltage of 100 volts supply. The first thing we're asked to find is to find the resonant frequency, so FR. So resonant frequency, as we saw earlier on, is 1 over 2 pi the root of LC. So this is equal to 1 over 2 pi the root of the L, our inductance, is 80 times 10 raised to the power minus 3 multiplied by the capacitance 0.25 times 10 raised to the power negative 6. Okay, so if we compute everything we have here into our calculator, our resonance frequency is equal to 1.125 kilohertz. So this is what we are going to get as our resonant frequency. So II, the current at resonance. To find the current at resonance, we establish the fact that V is equal to IR when we have a resonance in an RLC series circuit, so we don't need to find Z, which is the impedance. So from here, we can make current the subject. So if we make current the subject, we have voltage on resistance, and this is equal to our voltage supply is 100 over here, and then our resistance over here is 12.5 ohms. So 100 divided by 12.5 is going to give us 8 amperes as our current. So let's look at III. How many times greater than the supply voltage is the voltage across the reactance, or the reactance at resonance? So there are so many ways that we can find this, so we are going to be finding it one after the other. So the first one we can do is, this is Q factor. The first way is to use the formula direct, so 1 over R the root of LC. So this is equal to 1 over the resistance is 12.5 multiplied by the root of our L is 80 times 10 raised to the power minus 3 over our C is 0.25 times 10 raised to the power minus 6. So this is equal to, if we multiply everything we have over here, we are going to get 45.25 volts as our Q factor. Now another way we can go ahead and solve this is when we use the definition, the normal definition of the Q factor. So let me get some space and let's look at that. So another way to find our Q factor is equal to, we said that Q factor is the ratio of VL, the inductive voltage, over the supply voltage, and we also saw that that can be equal to IXL over IR, and that is equal to XL over R. And we said that our XL is 2 pi resonant frequency L over resistance. So this is equal to 2 pi. The resonant frequency, as we've calculated, is 1.125 times 10 raised to the power 3. Then multiplied by our L is 80 times 10 raised to the power minus 3. All on the resistance over here, 12.5. So it's 12.5 ohms. Then if we compute 2 pi multiplied by the frequency multiplied by this divided by 12.5, we are going to get our answer to be 45.24 volts, which is actually also the same as the first answer we got over here. Or we can also say Q factor is equal to VC over V, and that is equal to, we saw that earlier on, that if we do that, we are going to have 1 over 2 pi resonant frequency CR, and if we do that, 1 over 2 pi multiplied by resonant frequency, which is 1.125 times 10 to the power 3, multiplied by our capacitance, in this case is 0.25 times 10 to the power minus 6, multiplied by the resistance, which is 12.5, we are going to still get the same answer, 45.24 volts over here. So we realize that for calculating resonant frequency, whether you use the voltage VL over V, or you're able to break it down to 2 pi FR L on R, or you use VC over V, or you use the general formula, the inverse of resistance multiplied by the root of LC, you are still going to get the same answer for Q factor. So there are so many ways to calculate Q factor. You just have to select the one that is best for you, or the easiest way that you can identify it. So let's have a look at another question. So we have a series circuit comprises of a coil of resistance 2 ohms, an inductance of 60 millihenry, and a 30 microfarad capacitor. We have to determine the Q factor of the circuit at resonance. So this is also very easy. So let's go ahead and look at that. So let's write down our solution. So we have a series circuit comprising of a coil of resistance. So our resistance is 2 ohms. We have our inductance L is 60 millihenry. We have our capacitor having a capacitance of 30 microfarad. So we have to determine the Q factor. Now, like I said, there are so many ways to find Q factor. So let's go with the obvious one. So the easiest one is for us to say Q factor is equal to 1 over R multiplied by the root of LC, and this is equal to 1 over 2 multiplied by the root of L is 60 times 10 raised to the power minus 3 on 30 times 10 raised to the power minus 6. So if you do that, we are going to get 22.36 volts as our Q factor. Or we can find the resonant frequency first. So resonant frequency FR is equal to 1 over 2 pi the root of LC. So if we do that, we have 1 over 2 pi the root of, our L is 60 times 10 raised to the power minus 3, multiplied by our C is 30 times 10 raised to the power minus 6. Then if we compute everything there, it's going to give us a resonant frequency of 118.63 Hertz. Now using this resonant frequency now, we can calculate our Q factor by saying our Q factor is equal to XL over R. And then we know that XL is 2 pi the resonant frequency L over R. So this is equal to 2 pi multiplied by the resonant frequency 118.63 multiplied by our L, which is 60 times 10 raised to the power minus 3, all divided by the resistance, which is 2. And if we do that and we do the computation, we are going to get 22.36 volts as our answer. Or we can say Q factor again is equal to XC over R, which is equal to 1 over 2 pi resonant frequency RC, and this is equal to 1 on 2 pi multiplied by 118.63, which is the resonant frequency, multiplied by our resistance, which is 2, multiplied by our capacitance, which is 30 times 10 raised to the power minus 6. So if we do that computation again, we're also going to get 22.36 volts. So there are 3 different ways to calculate the resonant frequency, the Q factor. You can use the formula straight ahead to get your answer, or you can find your resonant frequency and use it in this formula, XL over R or XC over R, to also get your resonant frequency. So let's look at one more example. We have a coil of negligible resistance and inductance 100 millihenry is connected in series with a capacitance of 2 microfarad and a resistance of 10 ohms across a 50 volt variable frequency supply. We are to determine the resonant frequency, the current at resonance, the voltage across the coil, and the capacitor at resonance, and then the Q factor of the circuit. So let's go ahead and look at this. So let's write down our solution. So let's list our parameters. We have an inductance of 100 millihenry. We have a capacitance of 2 microfarad. We have a resistance of 10 ohms. We have a voltage supply of 50 volts. And we're asked to first of all find the resonant frequency. So let's do that. Resonant frequency FR is equal to 1 over 2 pi the root of LC. So this is equal to 1 over 2 pi the root of, our L is 100 times 10 raised to the power minus 3, multiplied by the C is 2 times 10 raised to the power minus 6. Then if we compute everything we have over here, we are going to get the resonant frequency of 355.88 Hertz. Okay, so now that we have the resonance frequency, let's look at II. We have to determine the current at resonance. So the current at resonance is equal to voltage on resistance, and that is equal to, our voltage is 50, our resistance is 10, so this is equal to 5 amperes. So let's go ahead and find the third one, III, the voltage across the coil and the capacitance at resonance. Okay, so we're told that the coil has a negligible resistance and then inductance. So because it has negligible resistance and only inductance, it means our voltage across that V coil is equal to IXL, and that is equal to, the current is 5, and then we know that XL is 2 pi resonant frequency L, and that is equal to 5 multiplied by 2 pi. Okay, let me make this bigger. Our resonant frequency over here, we said, is 355.88 multiplied by L, which is 100, times 10 raised to the power minus 3. Okay, so this will be equal to 5 multiplied by the 2 pi multiplied by the resonant frequency multiplied by L will give us 223.61. Then if we multiply that by 5, we are going to get 1108.03 volts. So it's 1118.03 volts as our V core. And then we can go ahead and find the voltage across the capacitor VC. VC is equal to IXC, and this is equal to I. XC is, this is I current multiplied by XC is 1 over 2 pi FRC. So this is equal to 5 multiplied by 1 on 2 pi multiplied by the resonance frequency 355.88 multiplied by the capacitance, which is 2 times 10 raised to the power negative 6. Okay, so if we multiply everything we have over here, we're going to get 1118.04 volts. Okay, so we have our V coil, we have our VC over here. So that is the voltage across the coil and the resistance. So let's look at IV, our Q factor. So the Q factor, we can use, we know that Q factor is equal to either VC or VL over V. So this is very easy. We can just use 1118.04 on the voltage supply, which is 50, and then that is going to give us 22.36. Or if you like, you can use Q factor is equal to 1 over R, the root of L on T, and you realize that we are still going to get the same answer, 22.36 volts as your answer for Q factor. So thank you so much for watching, and then I'll see you in the next video. Bye bye.